Good morning, everyone, and good evening in US side. So today is the second webinar in our ISPRS Technical Commission 3 Working Group 7 on Hydrosphere and Cryosphere. And this webinar series is jointly being organized with the International Society of Photogrammetry and Remote Sensing and Indian Society of Remote Sensing. So today we have one of the most renowned and well-known experts in the field of satellite remote sensing, Dr. Prasad Thenkabail from United States Geological Survey. And we are honored to have you on this webinar, sir. And for those who know, sir, sir has been with us, Department of Space National Remote Sensing Agency, in early part of his career. So he also knows most of us very well. So Dr. Thenkabail has conducted pioneering research in the field of hyperspectral remote sensing of vegetation and in the global croplands for their water use for the water security. And in the hyperspectral remote sensing, he has done cutting-edge research with wide implications in advancing remote sensing science applications in agriculture and vegetation. And this his work has led to a number of peer-reviewed research publications with very high impact. And in studies of global cropland for food and water security, he has led the release of world's first Landsat-derived global cropland extent at 30-meter resolution, and also global rainfed and irrigated remarkable books which are very popular among the user community, the handbooks on the remote sensing of water, urban, and atmosphere. So we welcome you, Dr. Prasad, and we are lucky to also meet you in person in 2022 and also in 2023 when you visited India for under US India program. So welcome you, sir, and the stage is yours, sir.
Okay. Thank you very much, Dr. Thakur. I appreciate your kind words, and it was always wonderful meeting you all at ISRO centers like IARS, NRSC. So I enjoyed those visits. As you said, I started my career at at National Remote Sensing Agency, now National Remote Sensing Center. So I have a lot of interactions with the Indian Space Research Organization. So, having said that, I will just jump into my lecture, and just let me know that whether you guys can see. Can you all see my lecture? First slide.
Yes, all good.
Yes. Okay. Very good. So then I will go ahead and start this lecture. Do you know how much time I should speak?
Sir, you have 45 minutes to 1 hour, and then we have last 10 minutes for the Q&A
Quite,
session also.
okay, very good. That's quite ideal. Thank you very much. So what I will speak today is about mapping the world from satellites, helping us understand, basically focused on food and water security in the 21st century. I want to also acknowledge some of my wonderful colleagues, Partha, Adam, and Et and Daniel. And if you look at many of my papers, you will see them as well. So, why do we need global croplands? The global croplands is basically tied up to all these issues. That is food security, water security, virtual land and water. I will go into a little bit more detail on all of this in the coming slides. Climate change, feed for the animals, nutrition, economy and energy, and population. So, as they say, agriculture is actually backbone of any country. So, without food, we don't survive. But for food, takes a lot of water to grow food. So, but we can look at and see everything from satellites and try to understand and map them. I want to give a context here. Start with the population. The world population for last 12,000 years, how it has. This is a data from the history of database from the global environment. Now you are looking at about 9,000 years back, and you see Mexico, China, Brazil, India. These are leading countries, and you will see how population in the world is changing. And now, as you come around 7,000 years, India and China are the two major countries in the world in terms of population. And this is a very interesting graphics to understand everything that we do with in context of water, food, land, how do we use land, and about our economies and etc. Now you can see here, now when we come to nearly 2000 years back, India, China mostly dominating the world population. If you put those two countries together, it more than the population of the other countries of the world. And this is about, you can see how many millions of people. Of course, now India itself has 1.4 billion, but even at 800, about 1,200 years back, how the population was, its population is always a flux. And you can see here what's happening with China. It goes up, comes down, goes up, comes down. And India is one country which has kind of uh, always had a large population in the world. And now when we come here, now you can see here United States actually only in last 150 years its population really jumped up. It's now coming, and now coming into third position. And now again, uh, you can see this dynamics almost as we come to the end of the last millennium and entering into this millennium. And of course, this is not quite up to date. Now you can see that um, that now, of course, the population of India just has overtaken China. So, but how did we feed the world's population? If you look at this map, this is a very interesting map of last 5,000 years of global cropland. And this comes from all these different literature. So 3,000 years back, just about 36 million hectares, mostly in Central Asia, Southeast Asia, etc. And as you can see here, how based on wherever the population is, croplands are taking. And even if you come to something like 1,500 AD, almost the Western continents, basically the US and South America, were completely almost blank. And so of course Mexico had some croplands, but now at the end of the last millennium was 1.5 billion hectares, and our recent maps using satellite data shows about 1.8 billion hectares. So that is 1,800 million hectares of cropland, which is about 13% of the terrestrial area of the world. So how did we feed the world with all this population growth? So what we call as green revolution. What is green revolution is that there has been a continuous increase in per unit land. The yield kept on increasing for each crop from, for example, from 1960s. So soon after, the Second World War, the peace dividend is that, people started living in peace, the population grew, and the population went from 2.5 billion at the end of the Second World War to now nearly 8 billion. How did we feed that? Basically, the so-called green revolution, which is a combination of factors. That is, the crop per unit area, the yield increased, the intensity of the cropping increased, irrigation increased, and both irrigation areas increased and rainfed areas increased. That is cropland expansion, irrigation expansion, cropping intensities, and how much you grow per unit of land. All of that increased. Just looking at the irrigated areas, because irrigated areas produce more food, from 50 million hectares at the end of the Second World War, now nearly, like more than 400 million hectares at the end of 2000. And in fact, we will soon publish this, that nearly 700 million hectares. Because what happens is, Irrigated areas is about how you define it. Definition is key to how you map something. That's a topic in itself, but I'll come to that a little bit later. So the other thing that is happening is virtual land and water. That means that you look here just to focus on and to give you a perspective. If you take Brazil, for example, which is 5 to 10 million hectares of Brazil land, is actually to whatever they grow here is to export to China and to maybe to Nigeria and to Europe, and US nearly 10 million to 27 million hectares of its cropland is actually exporting food to China and to other countries. So we are living in an interconnected world in which we are all interdependent, and somebody grows some food, and sometimes when you go and buy in markets, you don't know where that food has come from. And similarly, this also has an implication on water, because if you look at human water use, nearly 80 to 90% of all human water use goes towards producing food. And so if you look at US, for example, it exports 75 to 95 billion cubic meter of water. That means 75 followed by 12 zeros, liters of water, trillion liters of water is exported from here to Europe. And because the food is being supplied there, what is grown here. And same thing happening from Brazil. Brazil doesn't have a huge population, but it has a lot of land area, so you clear that land, grow for food, and but it takes a lot of water. But when you supply uh, food, you are actually exporting water as well. So the virtual food and water trade is an important factor. But how will we feed, how will the world feed itself going forward? So green revolution helped us overcome, as the population grew from 2.5 billion to 7 8 billion, we fed. But how do we feed the world? For the most projections show by 2100 we'll have 11 billion people in the world. My own assessment of looking at all the literature is that there are three areas where there are primarily we can increase food production. That is how much you produce per unit of water, that is crop water productivity, how much you are going to produce per unit of land, that is crop productivity, and how do you adapt ourselves to changing climate. So there are a whole basket of other things that come into picture, but these are the main areas where you can really start producing more food going forward. So we did a paper that one of my colleagues did a paper on crop water productivity of the world for all the blank areas where we don't have much data. But if you look at US and China and maybe Egypt and Turkey, they have high crop water productivity. That means for the wheat crop, what I am showing here is for wheat crop. That is how much you're going to produce for unit of water. So India is somewhere in between. India, Pakistan, and other countries somewhere in between, and many other countries are low. That means if you increase crop water productivity in countries where you have not really achieved optimal crop water productivity, you have option to increase food production. Yield gap, of course, is well known, and it comes from a lot of literature, wherein you can see here all these areas where what you are seeing in red and yellowish tones are areas where you have a lot of yield gap. So if you can increase yield in these areas to an extent of, for example, in Midwestern US, or for example, Haryana and Punjab in India, or in European countries, if you can increase, of course, you can meet a lot of food demands without having to increase the cropland areas, because both increasing cropland areas and increasing allocating more water for food, for growing food, is unsustainable, and potential is almost not feasible, I would say. So it is becoming very difficult. So you have to find ways of doing that without having to allocate more resources, both land and water, and by closing gap. But everything has its own uh, flip side as well, and that flip side can be, for example, how do you grow more food per unit of land? You have to put more inputs, and is it all good? We don't know, and if you are going organic, you cannot grow as much as if you are very industrial farming. So uh, one paper that came out by Snyder et al. Is showing that nearly 37 to 48% of the land can be reduced, and still you can grow enough food. But that has its own, you have to do a lot of heavy inputs, nitrogen and other fertilizers, herbicide, pesticides, and all that. So it will have its own implications. For example, do you apply more nitrogen into the soil, and what happens to the groundwater? Are you going to build more irrigated areas from rain-fed to irrigated? But where are the water resources for that? So this is a complex issue in itself, but it's uh, uh, so irrigated areas, there is roughly 75% of the world's croplands are, sorry, about 60% of the world's cropland are actually rain-fed, and 40% is irrigated. But 25%, sorry, 25% of the irrigated areas produce about 40% of the food. So irrigated areas have this great, higher production potential, but at the same time, environmental issues again come into picture. Of course, when I mentioned three possibilities: crop productivity increase, crop productivity increase, crop water productivity increase, and uh, climate related issues. But there are whole basket of things by which actually you can increase food production. And I don't have to read all this, but you can see there is a huge number of possibilities by which you can do. And in fact, I could add, how about utilizing artificial intelligence into that picture? So challenges of climate change, is another thing that we need to really ask questions. There are three basket of things that we can go. Can we grow more enough food from existing land? Can we grow enough food from existing water? Can we grow more food by reduced cropland by and reduced water allocations? But actually, these two questions are more important, because that is where we are headed. Actually, even if you look at the dynamics of the demographic dynamics in countries like India, a lot of people from villages moving into cities. So what that does is, a lot of croplands in the villages can get abandoned. So what happens? So you need to find various ways. So you'll have probably even less cropland going forward. And but then how do we go more food? So you need to find. So then you ask, how much more croplands are required? And if there is more cropland that is required, is there more cropland really, or do we have to intensify cropland? All these questions. And then, even if you are able to find answers to all of these, what happens if there is a pandemic? And what happens if there are wars and disasters? We also have to consider these kind of extreme scenarios, as we are seeing in the present day world, how situations are changing every day. But the current situation is that there is 1.8 billion hectares of cropland. If we need more croplands, where do we get that from? Ask that question. So I would even advocate that, the only way you can grow more food is through by reducing cropland and reducing water allocations for cropland. So we need to find solution to find, to address the need based on less resource allocation, both land and water. So, and also be prepared for any disruptions that might come along. We can't be caught surprised, like as we are in pandemic. And all sorts of other things. The other thing is, of course, climate. If these climate projections, if you just look at it, just watch US here, where we are currently, to where we will be at the end of the century from various global and regional climate models. It will get hotter, and if it gets hotter, then what happens is that to grow more crop, you'll need more water. And where do we get that from? And also, I was interestingly seeing this a country like India at the end of the century, at least from this projection, shows it gets more wetter, uh, not drier. Actually, that I thought was very interesting. But the other thing that happened at the end of 2010 was, for the first time in the world, see, crop always we produced more food by cropland expansion. Now, at 2010, for the first time, the cropland expansion kind of stagnated, and we produced more food through intensification. So, in the existing cropland, we started producing a second crop or a third crop, short duration crops, so that we can grow more crop. And so if you to give three examples here, if you look at Brazil, it is expansion is cropland expansion is taking place to, to is increasing, and also intensification is also high. So if you look at this color, IH is basically indicates increased expansion, and intensification is also high. But if you look at China and Southeast Asian countries, it is SH, which is expansion is almost stabilized, intensification is actually high. So that means more than one crop is grown. If you look at US and India, for example, it is SM, which is basically stable. Expansion is almost stagnating. Intensification is moderate. So, so all sorts of dynamics come into picture, which is also very an interesting thing to study. So far what I provided is kind of a background to what I will present going forward in terms of global mapping, bringing remote sensing and others, other type of data. So I will give one example today. That is to map the global croplands using USGS and NASA data. So at a planet scale, and through cloud computing, automation, machine learning, and basically at the highest possible resolution, that is 30 meter. That is we usually Landsat, but often we use Landsat and Sentinel as a combination. For example, if you look at the HLS data, that is harmonized Landsat and Sentinel data, which includes both Landsat and Sentinel data, and that can be provided either at 30 meter or at a lesser resolution, but the frequency of occurrence of this data can be less than 5 days for the entire world, and the HLS data is available for the entire world through USGS. So global croplands so what cropland products are needed? So if you look at it, if you want to understand global cropland, there are various products we can, what I call as primary products. That is, what is primary product? The primary product are where are all the cropland, which is cropland extent. Where are irrigated or rainfed cropland? And that is basically looking at uh, you know artificial supply of water or natural supply of water, irrigation and rain fed. And then where are all the major crops? For example, if you take wheat, the wheat dominates nearly 22% of all the global cropland. So if you have 1.8 billion hectares, wheat is actually 22% of that, and leading 8 crops of the world are these. And you can also see the percentages. And that is the fourth product. And the third product is actually cropping intensity. That means if you look at any given point, whether you are growing one crop, two crop, three crop, or a continuous crop, the continuous crop is plantations usually. So these are primary products, and doing a primary products very well is important, because Ultimately, you want to go to a single farm anywhere in the world and look at what is the spatial variability of this farm in terms of, you know, crop plant productivity, how the water is being used by to grow that crop, all sorts of these parameters, biophysical, biochemical parameters, you can actually get into farm level, individual farm level, anywhere in the world, and can study individual farm for all these parameters. I'll not read this. I am pretty sure you can see all these parameters. But if you have the primary products that I showed in the previous slide mapped very well, then the secondary products are much easier to develop, more accurate to develop. So in the 21st century remote sensing, you have all these different type of satellites that orbit the planet. There can be, Landsat, Sentinel. There are a lot of IRS, the Indian remote sensing satellites, Resource Sat, and other satellites. And then there is Radar Sat, and basically radar-based satellites, and there is water-based satellites, and so all sorts of satellites and sensors collecting data. And the modern day world is, it doesn't matter what data is collected from which satellite. You try to optimize that by actually some kind of a synthesis of different satellites and sensors, data from different satellites and sensors, and then put them together, especially in the cloud platform, and harmoniously analyze them. So what happens, for example, if you look at here, this is the planet data. So the planet scope has DAOs and super DAOs, which is actually about 3 meter resolution data. So if you click here, you can see this is almost, if you look at the time lapse, every day you are acquiring these images at a 3 meter for the entire world. And the detail that you see is like any given point, you can see here that, this is a time lapse image, so you can basically look at any given point and see how it is changing over time, spatially, just for visualization as well as for other ways. Of course, now we have a lot of hyperspectral satellites. Nmap, the German Nmap, was recently launched, and the data has started becoming available. There is Prisma. Thesis was on International Space Station. Earlier we had, for example, we had Hyperion data, which collected data from 2000 to 2015, and about 83,000 images are available for USGS, for free of cost for anybody. So at least you can do a lot of this work and be prepared for all the upcoming hyperspectral. And the Planet Labs also launching Tanager, the hyperspectral satellite, soon, and I think planned for this month actually. So you have high spatial resolution data and high spectral resolution data. And so let me go and say, to produce at least one product today in this lecture, all the different products can be produced using similar or slightly different principles. The first thing we need to know is a definition. If you want to produce a global cropland extent product, we made a simple definition. Anything that is standing crop, or even if it is not standing but the land is prepared for, is eligible to be cropped. Sometimes they might leave it as a fallow, and that's how it looks in the image. A cropped area might look it like that. And sometimes you have plantations also. So when you combine all this is what we call as cropland. So, in terms of methods, we have been mapping what I call as a paradigm shift in how we do global cropland mapping. One is having a series of satellites and sensors, and having the ability to process all this data seamlessly. This requires harmonization, standardization of the data. First, get the data from all of that, and then do what we call as analysis ready data. Landsat data, Sentinel data, IRS data, you can stack all the data, optimize as many satellite data as possible for getting the best of spatial, spectral, and radiometric resolutions. and then of course use the various machine learning algorithms, like for example random forest, support vector machine, or object based. This is a pixel based supervised classifiers, and hierarchical segmentation is an object based classifier. So you can use all that, and of course you can automate it, use machine learning and artificial intelligence as well these days, and then come up with cloud computing platform. You can for example in Google Earth Engine or Amazon Web Services, or even your local cloud, you can write scripts in Python, JavaScript, and then basically process your data for anywhere in the world. So the approach that we have adopted is to break the world into different agroecological zones, and these are basically based on the climate data. So each zone will have a long-term 100-year probably precipitation, 100-year temperature, and based on all that, and soils and elevation and all that, and you can compose that, break them into different zones. Actually, the Global Agroecological Zone project from UNFAO provide this about 300 plus agroecological zone, which we reduced it to some 74 convenient zones. And for each zone, you compose this kind of analysis ready data. So that will a stack of data for multiple years data. You can stack them. For example, here for a period of 1 to 60 Julian date in a year, you can stack all this data for different bands, and then of course you can do various type of processing like maximum value compositing and all that, and then fine tune it. And of course there are going to be clouds and other issues which you can write some kind of codes that using, if there are some anomalies in the data, you can fix that by using peak counting technique, simple codes that you can write uh, seamlessly across different areas. But what is required is also, remember that always we require a very good reference data to really to do the job very well. And you can see here we can collect this kind of data for the entire world. What is this reference data? This reference data can come from uh, see, ultimately your reference data has to be very accurate, and it can come from very high resolution data like sub-meter to 5 meter data for cropland, no cropland, or it can come from ground visits and ground data. So we wrote an app for this, and this app, what it does is, here what we have is a 3 meter planet scope data for this image. For example, this red point here is a cropland, we know by just looking at it. And every 2 months, yeah, you have a composite here. This daily data composited into 2 monthly periods. So you have, in a year you have 6 composites like that. And then based on the interpretation in the app, we can enter all the data, different type of parameters, and we can also know the intensity just by clicking at this point. Background will tell you, okay, this is the crop starts here and ends, gets harvested here. We can get to know what is happening in that particular farm. So, for example, for Africa, we collected all this data. Uh, so when we have unsure, so we say unsure data. So we are very good sample, 100% sure we are. And so I would say it is always not the quantity of the data, it's the quality of the data that you use in your machine learning algorithm. So this is very important to know. So and also ground data that you can collect, and all this type of data. Once you collect this data, what is required is a good machine learning algorithm. For machine learning, you need a good knowledge base. So based on thousands of samples that you collect, you create a knowledge base. And what is this knowledge base? This is non-cropland and this is cropland. A particular pixel might not be separable between the two here, but as it moves along during the growing season, it will move from here to probably here to probably here somewhere. So that gives an option for us to really separate these type of this one. And Similarly for irrigated and rainfed. And remember, this is done for each one of the 74 agroecological zones that I was mentioning earlier. And so what happens is then you use any, in fact, if you look at, we have written some series of maybe about 15, 17 papers on this. And if you go to our website, you can look at all these papers out, and all of them are downloadable. And all these algorithms are not, I did not just put it just for sake of putting it. And we have actually, if you look at our papers, we have used almost all of these algorithms in our papers. And to really establish cropland and no cropland, and just to show for Africa, random forest support vector machine HSEG, which is basically an object oriented classifier. So this is the image that you are seeing, and this is a random forest related, this is a object based classifier, and this is the final product that you get for any given location. And that is converted into a global map. I know because of time I can't go into too much details here, but for each zone you do this kind of training of knowledge base based on your reference data, using your uh, pyramid data layers. And then what happens is you get a global map, you can all stick them together, and finally we have about 1.87 billion hectares of cropland. Of these, 13% is cropland, and non-cropland is 87%. And and then of course you can zoom in, and at the end I'll show you how you zoom into all this and look at, you can look at actually individual uh, uh, farms, and then actually study them. So this is just few zoom ins to this one. And so what does that mean? So each one of the 74 zones we do an error matrix. And what error matrix does is, this is a data that is never used for training, that is only used for validation. And that validation basically says, if you take this North African zone, that yeah, the producer accuracy, which is errors of omissions, is only about 9%. The producer accuracy is 91%. That means we have captured the cropland with about 91 or 92% accuracy. But we are also saying users accuracy means that is non-cropland coming into cropland is about 11%. This is a trade-off you always have. People often project overall accuracy. I'm not that interested in overall accuracy, because overall accuracy can be influenced by non-cropland, which is a large portion of the area. What you really look at is producer and user accuracies of each class, how well that particular class is mapped. And here our interest is cropland class. And so this kind of accuracy is being done for each one of the zones, and that is converted into map, this accuracy. For example, anything that you are looking at overall accuracies is 90-91%, is all this dark area, and so on and so forth. But producer accuracy shows basically how well you have mapped a particular class, and 90 to 91% is where some of these areas, and some difficulty in fact, this one, and in our version 2 maps will have far more accuracies even for these zones. uh, and of course user accuracy. And what happens is, once you produce this kind of product, it has multiple applications. And like, for example, area statistics, you can, so for example, look at 180 million hectares and say, okay, how much does India has? About 9.6% of the global cropland area. So how much does China or US or Russia has? That's between 4 to 9% of the area, but is, but much of this is about 160 to 175 million hectares of cropland. For each country you can do that. The other interesting thing is, what is the cropland area per geographic area of the country? For example, you see a country like Ukraine has about 75% of its geographic area under cropland. Now, due to the war situation there, what happens is, how important, because it supplies some food to nearly 26 countries. Nearly 50% of their mainly grains are coming from Ukraine, and now due to supply chain issues, that's very hard to do that. And but then where do you cover? But country like Bangladesh, for example, not only has about 73% of its geographic area under cropland, but it has second crop and a third crop due to climate allowing for it. And other countries, Uruguay, and so you can see here. And for example, India is about more than 50 percent of its geographic area is under cropland. Hmm. So of course, Russia about 155, USA one. This is net cropland. Net cropland is where you have area equipped for cropland, but then you can grow second crop and third crop sometimes, or continuous crop. That is a separate issue in itself. Hmm. Here I did a plot from India's district statistics with our data, and you can see here how they pan out. Hmm. And this is for China, their provinces versus our data versus Chinese cropland data from the national statistics. You can use this data to many other type of purposes. How much land per person? For example, Uruguay has about 2 to 3.4 hectares per person. So it's for population, it has a lot of land in terms of agricultural area. US has about zero point 0.5 to 1 hectare per person, whereas India, for example, 0.11 to 0.25 hectares per person. You actually can gather exact number. This is a range map that we have created, but you can also get exact number from the statistics. Of course, I'm not going to speak about all the products, but just to show, when we produce these kind of maps, there is a very great detail in which we produce. What it means is irrigated, that is double crop, and mostly dominant in Nile, which is 2.6%. That means there is nearly 50 million hectares of cropland in Africa, out of each one of these class, and they have their own signatures, and we release this data through NASA LPDAC gateways, and you can get those kind of details for people who need this. And say similarly for rainfed cropland, and you can further consolidate that into single crop, double crop, triple crop. See, for Africa, out of 50 million hectares of irrigated cropland, much of it, 75% of that is single crop. That means you can grow crop once in a year. Africa has about 263 million hectares of rainfed cropland, and much of it is also single crop. That means you grow crop only once a year. And because otherwise there is no water there. So here is a irrigated and rain-fed map that we have produced, which we have already released on NASA's LPDAC. We are also producing a second version of this, which will be also coming out in coming months. US, for example, will be our first focus to produce the next version, which will be probably at 30 meter, which is at 30 meter, and probably the most accurate map you'll see. Of course, there are other type of products that we are also producing now, which is crop type. For example, for crop type, we are using neural network perceptron model, which I will not have time to go into. But again, you have lot of data cubes that you compute and use a training data. And US, it is quite ideal to train it with the cropland data layer from USDA CDL, and all these data layers that are basically nothing but the bands of data will basically look at uh, the training data, and then try to create different layers of data in a hidden layers, and then finally come up with, for each crop it will produce a layer, and then we can put all of this into a single map, which will show this. For example, we generated for an independent year, which basically shows cropland data layer from the reference data and what our algorithm produced. You can see here there is a lot of good match. And when you produce this for an independent year, that shows that your model is doing well, and you can apply it to other years automatically without having to go through all the processing steps that we do each year. In terms of dissemination, We have croplands.org where we disseminate at least for visualization, and there is a number of papers that actually you can go into this site and look at about our 15 papers, but also a research professional paper which kind of summarizes all the methods and techniques that are used. And of course, there is a website for the project. There are products that are released on the NASA selfie DAC, which you can download for the entire world, tile by tile, and stick them together, both for cropland and irrigated and rainfed. These are earlier product and browse and view. Uh, our data is used by lot of different countries. Nearly 100, more than 100 countries use our data every year. So this is slightly dated. But before I end my lecture, I want to show you something, uh, uh, something more, which is uh, just it will take me let me say 2 5 minutes of demo. So you can go into croplands.org and look at our product. Just for example, if you zoom into India, for example, you can go in here. Any randomly, I'm just zooming into some place, and you can see here. You know, you can see here. So it is, if you take out, you are actually looking at individual farms here, and this is all the green is irrigated area. And if you want to look at, let us say I want to look at 2000 to 2024, what is happening here? Sorry, I'll just click this and say show me what is happening here in terms of ndvi. You can see here. Now, the interesting part of this is, if you look here, you see here, this is 2018 February, 2017 August, 2017 February. So you can see here continuously it is mapping anywhere in the world. You can do this, and uh, using, for example, you can go into some other area, just because I think the let us say I saw an audience from Australia earlier, and this is, I think, Murray Darling Basin or something, irrigated area. So you can basically look at this, and you can go into any one of this area and then just click on this particular point. And so for 24 years now it will generate continuous, and you can see here what is happening. In some years it is doing good, some years not that good. And if you put a shorter timeline, something like, let us say, just 2020 and 2021, sorry, just 1 year. So if you do 1 year, you can see here what is happening. So for that particular point, so you can basically look at, every month what is happening. And that's really interesting. And that is not limited to one product. For example, you can go in and change from, okay, I don't want to look at uh, uh, so sorry. So if you go and look at Landsat data, so earlier irrigated and rain fed, if you remove that and say I want to just look at now cropland extent, you can look at just cropland extent, and again for the entire world it comes. And there some products might be a little bit regional, like Africa. We have a product that is, let us say, uh, for different years in very very detailed mapping for Africa for different years, United States, Australia, like that. So I think I'll stop here and basically let you guys ask questions. Thank you.
Thank you, Dr. Prasad, for the excellent lecture.
Yeah, most welcome. Thank you.
Thank you, sir. Very elaborative lecture covering all types of remote sensing.
Yeah, go ahead.
वैभव आपकी your voice is breaking.
Yeah, I can hear you. I can't hear. Okay, go ahead. Please.
I think the connection is not very well, but probably you can proceed with the question and in the Q&A box. I think there are 6 questions right now.
Okay. Yeah, in the chat.
Not in the chat, in the Q&A box. In your
In the Q&A box.
there
Okay.
you go. There you go.
Okay. So when stacking multiple data sets, how is non-uniformity in spatial resolution taken care of? It's a very good question. So see, there is, of course, this is kind of a fundamentals in remote sensing, which is geometric correction, radiometric correction, data, intersensor relationship. First of all, you need to build intersensor relationship between two sensors when we are doing how to how their reflectance are correlated and all those things, and then you have to resample using any of the techniques, nearest neighborhood or cubic convolution or whatever. You have to process all that. All of this can be done with coding in Google Earth Engine, for example. That's how at least we have been doing, because it's quite seamless. You have all the data there on the background, the Landsat, Sentinel, and all that. So we bring them together and we start off with, first of all, are they normalized to ground reflectance? So is the data at top of the atmosphere reflectance, or is it converted into ground reflectance? So once we have that established, we look at the spatial resolution of these sensors, and then okay, so if something is at 10 meters and we want to resample that into 30 meter and bring them together, and all that kind of thing. So that's how we go. I will go through each one of these questions, and I wish there was more interactions, in the sense people could ask and maybe follow up, but unfortunately it looks like I can't. I'm not hearing anybody anyway. The next question is, usually validation data comes from direct field measurement or other independent source, which is different from data under observation. How satellite, sorry, uh, how satellite data can be used as validation reference data as our observe. See, what happens is, as I said, of course, there are various approaches of collecting data. In the app that we have developed, what it can do is, for example, one example is it can randomly spread data points for the entire world at a 3 kilometer distance, at intervals, I would say. Every 3 kilometers. That is something you can set it up. You can say randomly spread out 3 kilometer or 10 kilometer or 5 kilometers. So what an interpreter can go in and say at any given point, what is it? Is it cropland, non-cropland? Especially using sub-meter to 5 meter data, you can easily see whether it's a cropland or not. If there is, of course, if there is an uncertainty, you consult an expert, or you just drop that point there, because there is no certainty even from an expert. Of course, ground data to substantiate that is very important. A lot of other data like cropping intensity can also be gathered from that. When you want data for irrigation and rainfed, you can get it either from secondary sources or from ground data, etc. But however you collect your data, once the data is of good quality and especially verified and collected very well, you split the data into three groups. One is the training data, which is used in the machine learning. That again is randomly split, maybe about 60, 20, 20 or something. And the 20% is mostly for testing. That means when you do a particular classification, you can use this point for verification whether that class is the class that you desire. And the final is validation data set that is independent. That actually I would even say in our case at least, it was not even the validation was not even done by the group which produced the data set. So it was done independently by a separate group, and the people who produced the data did not even have access to that data. So that kind of a thing. As you have shown in the map of per person per hectare, it's based on farmers or total population. It is based on total population, of course. Not based on the not based on the farmer. Where can you avail global irrigated and rainfed data layer? So if you, I'm happy to share my presentation at the end. It is all our data is published. One is you can go into croplands.org, you can at least visualize that. But if you want to download the data, there is what we call as algorithm theoretical basis document, user guide, and these are available at the NASA's LPDAC along with the data sets. So the entire world's data set is available at NASA's LPDAC. All you have to, even if you Google it by saying LGRIP 30, USGS or something, it will come out, or global GFSAD data, NASA LPDAC, it will also come up. But you can also get the link from the my lectures, and you can download this data. As I said, that our data is being used by more than 100 countries every year, so that shows a wide use of this data. Which hyperspectral sensor and ML algorithm are best used for methane detection? Okay, now the thing is, I would say that here we are not doing any. Of course, if you map rice, you can you can methane emission from the rice field is a big thing. But I would say you are not using, at least Landsat and Sentinels and all the data that we have used are not used for really methane. But you can of course use the hyperspectral data, and then you can also use the other sensors that are like OCO, data to do that kind of work. Here there is another question. Thanks, Dr. Thenkabail, helpful presentation. Is there some global centrally available data source that shows crop uh, growability in various regions under the climatic, RCP? Yeah, this is again a very good question. Uh, that you know what you are asking here is where are the potential zone for growing crops, and um, you know uh, at least we haven't produced such a map, but I would suggest that you may want to go and look at the agroecological zones. That basically gives you the potential zones where, because this is an agroecological zone, correct? So where is, for example, if an agroecological zone where there is a potential to grow crops in a 365 days a year, and that is a good area, at least in terms of climate, to for you to do that. But of course the soil and other conditions come into picture, but the agroecological zone map could be a starting point for you. uh, 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 Sorry, my my cat wants to okay, so the next question is, sir, going from finer to coarser resolution is understandable and easy, but how do you go from coarser to fine resolution through resampling? Um, yeah, in the sense, of course, for coarser to fine resolution, for example, from the 250-meter, you can resample to 30-meter, but that doesn't really going to really, of course, you can resample if you are going to work everything in 30-meter and you want time series data. you can, of course, fuse the two using the same principle, wherein you, instead of resampling from 10 meter to 30 meter, from 250-meter can be resampled to 30 meter. But that doesn't really mean that you are going to have different what you call NDVI or different reflectance for every 30 meter, because it is 250-meter data is a 250-meter data, but you will at least get a harmonized data. So there is no real real what you call you have to collect data at a final resolution. The coarser resolution data resampled into final resolution is done only when you want to work with multiple data sets but with one resolution. Yeah, how is harmonized data sets prepared? See, the harmonized data, as I mentioned, I think I mentioned at the very first question, is first you start off with whether, does the data come up with ground reflectance, which is the primary question that you ask, or is it at top of the atmosphere reflectance, or is it at radiance, for example. So you want to first of all make very clear, using whatever models that you use, 6S or whatever, you want to make sure that you convert everything into ground reflectance, and so that if there are two data sets or multiple data sets, they're all in one resolution. Then of course the synthesis of the resolution, whether it is 30 meter or 250-meter, you want to bring that into one resolution by resampling techniques. Then inter-sensor comparison, an NDVI or a reflectance of one sensor is not the same of NDVI reflectance of another sensor. So you have to develop inter-sensor relationship. And if you really look at some of the my edited books, we have covered a lot of these chapters, wherein we address, in fact, in the volume 1, just the issues that you just asked about.
Yes. Thank you, sir, for nicely answering all the questions. And I request all the participants to send a personal email to sir if you have any issue. And you can send mail to ISPRS or ISRS also. We will be interacting with sir directly and to share his answers. And next webinar will be on 12th of July. There is slight change on the date. From Wednesday, it is now shifted to Friday due to the availability of the expert. That will be on hydrometeorological hazards by Dr. S.P. Agarwal. So, Dr. Prasad, we just need your consent. Can we host your recording in ISPRS Student Consultorium?
Yeah, sure. No problem.
Yeah. Thank you, sir. Thank you.
Yeah.
So, very nice to meet you again, sir. And hopefully, we will meet again if you come
Yeah,
in
yeah.
India or if
Yeah,
we
yeah.
get a chance to interact in some international forum again.
Yeah, yeah, sure, sure. Well, I'm pretty sure we'll meet again. Yeah. Thanks for organizing
And
this.
just answer one request from our side. Uh,
Okay.
our students and the research community, they are very much interested in the crop type map.
Okay.
So
Uh,
they have been asking is whether it is feasible to give some broad level of crop type map, for example, wheat,
yeah,
sugarcane, rice, on
yeah.
annual basis.
At present, we don't have a global crop type map, but thing is, in fact, we have just submitted a paper to a journal on the crop type map, especially working in California using neural network perceptron model. And it is possible to automate especially if you have good reference data and if you build a model, neural network models, it is possible to develop this model and then apply it to independent years and get it. But our goal within this project is actually to at least map major crops of the world. Our focus will be actually for crop type US and India actually. So US and India, and I think in the coming years we'll definitely develop models for doing that. But at present we are doing it at I would say a very regional scale, a very small areas to test our models and build algorithms very well. And
Thank you.
and this paper, when it is published, I'm happy to share with you. I'll remember that.
Thank you. Thank you, sir.
Yeah, sure.
Thank you. We are
Very good.
closing the.
Okay,
Now
very
you
good.
can.
Thank you,
Thank you so much,
everybody.
sir.
And yeah, thank you.